So, hi, good morning. We are about to come to the last technical discussion of this nice week. And I have first an announcement, and then I will introduce this good man that is on my left. First announcement is for you to be more calm maybe in your time plan. For today lunch, you can go to the area of lunch as usual, but there will be also kind of lunch in a box for the people that has to leave, so you can take the box and you leave with it. So there is no need to rush because you have to stay then in the restaurant. You can take the box and go. And this gives us more freedom just to enjoy the discussion and to close well this fancy UCNC event. That's as an announcement. And then as a panel chair, I have the pleasure to announce the third and last panel, which is the most technical one, I have to say, because the other were more like future-looking and this one, but this is about something of facts, that is the future of artificial intelligence, and how artificial intelligence and 5G will merge. And we believe that this is the 6G. I mean, this that we are seeing here, the merge of the technology with artificial intelligence, and this was also the message of FedWise yesterday, this will bring us to the limit of the tactile internet, to the limit of the latency we can reach, and to actually get this millisecond that we need for these applications we foresee for the future. And the moderator and so good organizer of this panel is the Professor Panagiotis Demestikas. Here on my left is professor in his part-time in the Piraeus University, but he's also the founder and the CEO, right, or something like this?
Something like that.
So CTO of Wings, ICT Solutions, which is a company that yesterday got also the best prize for the booth. So congratulations. He will run this panel with this nice group of experts we have here. So Panagiotis, welcome and thank you.
Thank you for the kind introduction. The best booth went to the 3 projects, of course, but we are glad to participate, so thank you anyway. So the title, as you can see, is Beyond 5G and Artificial Intelligence. So these are 2 areas on which we have been working on. And so the key question, let's say, is whether these are 2, how much are they interleaved, how much are they coupled? Without further delay, I will, let's say, introduce you to how we have structured the panel, which as a matter of fact is several months of work and interactions with the panelists and also with the European Commission and the panel chairs. First, I will introduce the speakers. Then I will introduce a bit, let's say, how we came to the idea. I mean, what were the thoughts underpinning. Some key questions, that we have thought. Of course, the floor will be open to your questions or to your thoughts. And also, at the end, I will explain you how we will work through this slot, in terms of time scheduling. So I'm really honored that for the speakers and for taking their time to interact with us and to be here in this conference. First, we have Dr. Heli Helakowski. She's from VTT. She's a senior principal engineer, and she will be talking to us about applications and AI. She's an expert in that area, and I think this is an important area for us people coming from the infrastructure to interact and to see what we have to serve. So I'm looking forward really to Dr. Heli Helakowski talk. Second will be Professor Slavomir Stanchak. He's from Fraunhofer HHI and from the Technical University of Berlin. He's the head of Wireless Communications and Network Department in Germany. He will be giving us also some research challenges related to the problem. Third is Dr. Sana Benzema. She's from Orange. She's a research engineer and a project manager. She's an expert on self-organizing networks, cognitive networks, artificial intelligence-powered management from France. Fourth, we come towards the vendor, towards the, let's say, the provider of solutions. It will be first there will be Dr. Henning Sanneg. He is the head of the network automation department, Nokia Bell Labs in Germany. And last but not least, of course, is Dr. Pei-Ying Zhu from Huawei, from Canada. And we thank her very much for taking the time to be with us. So, how did we come to this idea for the panel? We can admit that B5G and AI perhaps are buzzwords, but on the other side, we must also admit that in Europe we have a deep-rooted tradition on several aspects, like wireless communications, telco expertise, and also expertise in optimizing networks. We know a lot about optimization algorithms and also on how to manage networks. And at some point in time, around 10 years ago, for instance, through the E2R, eCube projects, we came across the cognitive network domain managed by Didier, as a matter of fact. And there we came across to the machine learning techniques, and on this we kept building. And now, let's say we are in an area in which these machine learning-based techniques form the artificial intelligence world or a part of it, and we want to see how to exploit it. So let's say that there were several expertise sources, there were also several keywords, and we wanted to see whether the future of networks and of applications, what lies beyond, whether we can combine all this to deliver some new generations. When we decoupled the problem, we thought first of all to start identifying, to focus some talks on the architecture and on the network operations, what will be the impact by AI. But also, of course, not to forget, let's say, the application part, as I said. I mean, what will we have to serve? Can we do it today? Or what more is needed in order, from the networks to evolve or to introduce new components and support them? So all these thoughts that went on for some weeks, let's say, of interactions, finally led us to some questions that I would like to introduce first, let's say, as some key points, as some, let's say, an initial point of the discussion. We will take this discussion at the end. The first is AI for network optimization. I guess we will have some talks on how we can use AI for making better networks. Then turning to application aspects, there are many applications that leverage on AI. They need AI in order to operate. It's not only robotics, it's also other areas. For instance, water or energy. You need to predict situations based on advanced techniques in order to handle them and not let them happen. Or health, any domain has such requirements. So maybe there are requirements there that will not be served by the scheduled releases. We need to look ahead and then schedule further research then and standards. A topic that I like is that perhaps, network, we should try to have the network not as a bit pipe as we were calling, but perhaps with all the data it collects, maybe we can see the network as an ecosystem eventually that deliver higher level services like insights. For instance, localization information. Maybe we can combine it and then through network mechanisms have some components better for the application developer. The last 2 points I would like to introduce is whether do we have sufficient substance, sufficient material for heading for a new generation? My view is positive, of course, and also I think it was in the keynotes of the last days, but we would like to listen to your view and also to the panelists. And then final issue, which is also important, is the competencies. We need the telco, of course, expertise, but we also need the software expertise. And also a point that I would like always to say is that we need also sometimes the product guys and the business guys in order for all of it to work as soon as possible. So let's take these as 5 points that we can use as questions that we can pose to the panelists to see their views, but in addition to yours, and also your views. So in order not to steal more time from the panelists, how this will work. We had the introduction, my talk. Then for, let's say, the next hour, we will pass the floor to the speakers in order to make brief presentations through slides. And then if there is a burning question, we will be glad for the particular speaker. We would be glad to take it and to immediately handle it. And then at the end, let's say 30 minutes or whatever time remains, we can go back, open the floor to questions and discussion with the audience, and perhaps also address some of the 5 points I raised. So, without any further delay, I would like to invite Dr. Heli Helakoski to the floor for her speech. Thank you.
Okay, thank you. Thank you for inviting me here. Like I said, I'm from the application side, and this is a bit unknown area for me. So I come from VTT Technical Research Center of Finland. We are doing a lot of also 5G research, but I'm in the application side, and I work a lot with the industry. And my main work is to apply these kind of new technologies into industry, such as blockchain, 5G, telecommunication, artificial intelligence, and these kind of things. So we need to think about what is the benefit from these new technologies for the industry. And I will skip the slide from VTT. I think part of you actually know what is VTT. So, but the main point at the moment is that our world is changing very fast. We are facing the terms autonomous everywhere. This is a new term, not a new term, but now it's really developing because of the developments of artificial intelligence. In the picture you can see unmanned airport taxi, which is a kind of implementation of AI communication networks, new energy innovations, using new materials, using data analytics, and using semi-autonomous working models in a new form. This is a kind of new products, what kind of products we will see in the future, and these kind of devices, equipment will change our business life. They will form new kind of ecosystems. And the same thing is ongoing in factories. We are moving towards autonomous factories. First, we are automating some process points, but at the end we are connecting these process points, and that will lead us to more autonomous factories, where the role of human will be controlling and monitoring the whole process, but releasing the human from manual work and leave the more interesting things for human. All these developments, when we are moving towards autonomous systems, they will, of course, it's very obvious that we need artificial intelligence. It's underlying in all these developments, but we also need new sensors, new devices that are able to perceive the environment and analyze the information. And of course, we need new telecommunication networks, which are very efficient, can transfer the huge amount of data these kind of solutions need, and of course they need to be secure and reliable. Here's a picture about the industries that are evaluated that will be using artificial intelligence and 5G in the future. The picture is produced by Ericsson. So the most important things are the energy and utilities. They are using artificial intelligence and 5G, and also manufacturing. There's a huge expectation of the new technologies to develop these kind of industries more competitive and for providing new innovations. And also public safety is the one which is enabled by 5G. And it's quite obvious that these demand will raise. And also healthcare is one of the things where 5G can bring new applications, new possibilities. And then, as I mentioned in the first slide, the public transport. Our transportation system will probably move towards autonomous systems, and then the 5G and artificial intelligence and cybersecurity, they are really important in underlying all these solutions. There's some examples of the 5G boosted use cases. In manufacturing industry, there has been a lot of talk about predictive maintenance, and now eventually I think it can eventually be true, because we have powerful analytic systems, and furthermore we can transmit the information by using new telecommunication networks. So it means that we can fix before anything is broken. And then there's the robotics. In Finland, there is already case studies where ABB is researching how to use robotics in their production line. and it's related to quality management, that the system is perceiving the quality of the process delivered. And then the supply chain management. That means that there's a whole lot of companies sharing the same information, analyzing the same information with different kind of devices. And of course, artificial intelligence can integrate, provide more insights for this information, and it needs to be delivered for all partners. And the same goes to energy industry. We need systems to remote monitoring and managing the distributed electricity network, and of course we need to manage the energy resources. And the smart metering is one thing which is ongoing. And then I wanted to show you one case, because I come from Oulu. Oh, this goes really fast. Okay, so I come from Oulu. So we have a 5G test site in the port of Oulu, where we are building a kind of ecosystem where all the partners can collaborate and test the new application in port area. It's not only a port, there's a pulp and paper mill side, and this is a kind of network where the research partners and companies can make their first proof of concepts and use their imagination, what kind of capabilities 5G combined with AI can provide. Oh, so this is shortly from my side. Thank you.
Thank you very much. Is there some burning question from the audience for the speaker, or we can have it also at the end, but if somebody wants to point out something. I can't see something, so yeah, thank you very much. So I would like to invite Slavomir to the stand. Slavomir, as we said, comes from Fraunhofer and from the Technical University of Berlin, so he will give us the research perspective, at least, plus other perspectives related to the problem we would like to discuss today.
So, good morning, Panagiatis. Thank you for inviting me to this panel. It's a great pleasure to be here and share some thoughts with you. I took 3 slides out of my talk I gave yesterday, so sorry to those of you who attended my talk yesterday. I'm trying to convey the same message again and again. 5G and Artificial Intelligence panel. MLC stands for Machine Learning for Communications. So we are talking about here about machine learning for communications, not about machine learning or AI, only in the context of communications. So first of all, I mean, the question is why? Okay, so there are some entry points for machine learning-based improvements. First of all, I mean, currently we deal with networks with high complexity. So there are things for example, we don't have good models, right? And also, good model is relative. What does it mean? For which applications? There are applications, for example, in the industrial domain, where we don't have models that are good enough because they have so strong or so strict quality of service requirements. There are also issue of inefficient computation. You can think of about optimization, how to compute, for example, some quantities in networks with communication constraints. And we also develop algorithms with slow convergence. So we have to truncate, and then there are some problems. So there is something, we are not perfect. So, and that's why we are talking about AI and machine learning for communications, because we have solutions, but they are not just, optimal, and there is some need for improvements, right? Potential benefits, there is also here a list of benefits. Okay, I mean, we hope, for example, machine learning can help to cope with this increased complexity, reduce the number of measurements. For example, think about pilot contamination in wireless networks. Self-organization is an old topic, but still we are talking about this, and we still have humans in the loop. And prediction is also a hot topic, big topic, and of huge interest in industry. So think about quality of service quality of service prediction for V2X, for example, applications. So the first message I'm trying to convey is that machine learning is much more than deep neural networks. This theory is, we are talking about theory that is not new. I mean, it's at least 70 years old, and we were using it also in communications. Think about cognitive radio networks and things like this. This is about machine learning and AI. So the first message is AI and ML is much more than deep neural networks. So okay, but now why there is so big interest with something like hype? So this is, because we have, of course, more computation power, and through mobile networks and access to huge amount of data. And then there are deep neural networks, and then I took this figure from Andrew Ng. It shows that, the deep neural networks, they scale better or perform better if the amount of data increases, right? So, and we can see many applications where deep neural networks perform much better than traditional machine learning tools, but there are two key issues, or two problems, at least with this figure. First of all, I mean, energy efficiency is neglected. I think that energy efficiency in mobile networks is an important issue and has to be taken into account. And then also domain knowledge is ignored, usually. But we have a lot of domain knowledge. And this is the second important message I'm trying to convey here. And why is this important? Look, if you think about lower layers, I am mainly interested in RAN. So if we are at the Phi and Mach layer, the world is highly dynamic, right? So we have, fast time varying channels and interference as well. And then it's not only that, the channel changes, but also the distribution behind the channel changes. So we have highly non-stationary environment. So what would it mean? I mean, if we apply, for example, neural networks, it means that, for example, for applications like V2X, we have to retrain them every 40 milliseconds. I don't know whether it is going to work, right? So, okay, we also have to talk about distributed solutions, because we have data is captured at different locations, and we have communication constraints. And then also we have to take into account limitations of computational power and energy as well. If you go to higher layers, and I think that other speakers will mainly focus on higher layers, then I think that we may have access to huge data sets. So neural networks may be, good approach. But we have to cope with other problems like incomplete data and erroneous data, misaligned data. And the most important thing is we have to cope with time series. So this is, the second message I'm trying to convey, so that we have to differentiate, and we cannot neglect, traditional machine learning tools, because, we have some limitations in mobile networks, energy efficiency, and we have domain knowledge. And traditional machine learning tools may provide natural interface to include this domain knowledge. At the moment, we don't know how to include this domain knowledge when training deep neural networks, and this is a big problem. So the last slide, demands of machine learning for communications. First of all, robustness, and also online machine learning. So I think that, if you go to lower layers, deep reinforcement learning is also not new, of course, or reinforcement learning, game theory. You have to cope with this dynamicity you have at lower layers, and you have to provide robust results with small, uncertain data sets. Important thing is we have to exploit domain knowledge. And then that's why I'm talking about hybrid-driven machine learning. Not data-driven, not purely data-driven, not purely model-driven, hybrid-driven. Combine both worlds. And then this is extremely important. If you go to industrial communication, for example, we can take into account models, production, and communication data to get really great results. Another thing is you should learn features that change slowly over frequency and time. I don't think that machine learning is a good approach for channel estimation. But there are things, if we exploit our domain knowledge and learn, for example, angular power spectrum is another example that change slowly over frequency time, we have time to learn it in a robust manner. And then we have to preserve important function properties. This has something to do with robustness I mentioned yesterday in my talk. Distributed learning for efficient usage of scarce resources, low complexity, low latency implementation, we need solution that is amenable to massive parallelization, and also, of course, security, secure machine learning. This is especially a topic for higher layers. Thank you very much for your attention.
Very nice overview and very nice, excellent challenges. Some burning question for Slavomir, or we take them at the end? No need to be shy. No, let's take them at the end. So let's move to the third panelist, Sana Benzema. She, as we said, she's from the operator, and she will give us the operator perspective on how we could use the technologies and various positionings.
So hello everybody, good morning. So thank you Panagiotis for inviting me to this panel. My talk will be about artificial intelligence, and I will somehow describe the ongoing works in Orange Labs about this topic. So first of all, the first question that was risen is, okay, artificial intelligence and beyond 5G. So if you look at the plethora of use cases promised by 5G in the beginning, you can see that a lot of them are still ongoing. So we are still in the era of 5G. We can talk about beyond 5G, but in my opinion, we didn't solve all the open issues with bringing all these use cases together on the same infrastructure. So if you look at the Gartner hype cycle, you can see, for example, that autonomous driving is a use case that will reach this productivity plateau in 5 to 10 years. And in the automotive industry, we start seeing mechanisms that allow this system work, and we see artificial intelligence everywhere there. We see artificial intelligence embedded in cars. We see it also through communications between the infrastructure and the cars, and we see it also in communication between terminals in cars. So all this together shows that we will see machine learning somehow everywhere in this kind of application. And once these machine learning mechanisms will be defined, then we need to define the communication channels and the required communication between the infrastructure and the cars themselves. So we are in the beginning of a long journey to put artificial intelligence in networking on the applicative layer, but also as we have, so the question of complexity have been risen already, as we have to put all these use cases together on the same infrastructure. The 5G have been designed and is still designed with high flexibility. And from a management point of view, high flexibility means very high complexity. And to manage this complexity, we started talking about automation since 4G. We have already self-organized networks today deployed in several networks. And the next step will be artificial intelligence. So with self-organized networks, the concept have been defined to cope with operational expansion. So to just, in the beginning, we told about saving OpEx. And then we tested features and we saw that we have already gains on efficiency, on operational efficiency, and also on network performance. With artificial intelligence, we expect to have higher gains on performance as well. So what can we do with artificial intelligence in networking? So I go back to my domain, which is network management. So first thing that we can do is to observe the measurements that are reported by the different nodes of the network. We can observe, for example, to be able to characterize a normal behavior of the network, and then to detect an abnormal behavior, to detect anomalies, We can also observe trends. For example, we can observe an increase in traffic demand in time, and this will allow us to make decisions, for example, to add resources or decisions of densification. We can detect context shifts. So this is a very interesting topic because if you optimize the network, we optimize it for a certain context. The context includes the topology of the network, includes the traffic behavior, the user's behavior, etc. And if the context changes, our optimization is not valid anymore. So we need to be monitoring the network all the time to be able to detect context shifts and then to be able to put in place new optimization which is relevant for this new context. Then once I have observed the network, I need to understand the behavior of the network. So understanding the behavior of network means that, for example, we have some works on trying to understand the impact of the radio performance on the application performance. So I put here analyze correlation between KPIs. So key performance indicators. We have several key performance indicators, and by trying to understand the correlation between these key performance indicators, I can say, for example, the impact of the radio is high, so I need to optimize the radio. And to be able to optimize the radio, I need to understand also on which KPI I should act. And for this, I analyze the sensitivity of the KPIs to the different parameters on which I can act on the network. So I can determine the most impacting parameter and be able to optimize my performance accordingly. And also we have very, very large literature about root cause analysis. It's not enough to detect an anomaly. It's important also to understand the correlation between the anomaly and the most potential case. And then once I have observed my network, I understood its behavior, I can also use artificial intelligence to predict what will happen in the future. So I told about traffic prediction. So traffic prediction, for example, we have today a trial running in Spain in collaboration with Orange Spain and Huawei, trying to enhance the energy efficiency, I forgot the name of the feature, sorry, but anyway, we are trying to enhance energy efficiency based on accurate predictions of the traffic. I can also predict long-term traffic, as I said, to be able to densify the network, for example, on time. I can also predict in shorter term the load of the network. And for this, we have an example also of work, which is also under trial today in collaboration with Nokia this time, on enhancing the load balancing algorithm, because we have the load information that is reported every 15 minutes, and the objective of the algorithm is to be proactive and to be able to manage the overload before it happens based on predictions. Then we have a stream of work on spatial prediction. So as I said, we can predict what will happen in the future, but we can predict what will happen in the surrounding area based on measurements of some users that I can get in the network with their geolocation. So the geolocation is today a new source of information that have a very high potential in the network. And one of the applications for network management is to be able, for example, to build maps. So we have been talking about radio environment maps for a while. Today, with the increase of sources of geolocated data, this will come to the reality, because we have minimization of drive test features that starts to be available in the network. We have also embedded agents that report geolocated information, and we have also several geolocated solutions that rely on network geolocation And these solutions are built with a lot of analytics there to analyze the data and bring an added value to that. So all these aspects rely on the data that we can have from the network. And this data, from an operator point of view, comes from the suppliers' networks. So we need to understand what is behind each KPI. We need to understand what is behind each metric that is reported, and we need to access to this data. So, for example, in Orange, as we have several suppliers, we need to have common KPI definition based on the different counters definition coming from each supplier to have a global understanding of the metrics of the network, and this is a big challenge. So this is a big challenge related to openness, so accessibility to the data that comes from the network, because we don't have the same data coming from different suppliers, and also interoperability, because we have also over-the-top solutions that need data coming from different suppliers. So these over-the-top solutions, for example, are solutions related to geolocation solution, for example, and self-organized network solutions. So once I have done all this stuff with the data to be able to understand my network and to predict its behavior, I need to make decisions. And there are two ways of making decisions using AI. Either I rely on the knowledge that I have built, and I make a deterministic decision. So it's more the AI as a support to automated decision-making, or I learn online. And learning online is a very big challenge today, even in research, because, okay, we can run simulations using reinforcement learning, multi-armed bandit, deep reinforcement learning, and so on. But the problem is that if you bring this to the operational world, you cannot offer to fail on a real network. So we can tell, for example, operational people, okay, I have a very interesting algorithm that will succeed to find the best solution in 2 weeks. But in between, it will decrease the performance, for example, during half of the time, because it needs to explore. So the main issue is this online learning, and we will need online learning on the network, because we don't know everything. If you want to have this high efficiency, we will need to discover what happens in the network, because we cannot have this information in advance. We cannot have the reaction of the network to any possible configuration in advance. So we need to test and to try to enhance the performance online. But we cannot offer to fail. So this is valid in higher layer, especially where I have low reactivity. So I cannot test, for example, configuration that make the network performance decrease for 2 or 3 days. So this is the main challenge, and this makes this stream of activity rather in research today. We try to find solutions such as collaborative learning, transfer learning, or being able to pre-train the algorithms based on simulations that are very close to the network reality, and then transfer the model to the network. So we have, I would say, short-term use cases that can be already operational under testing or trialed, and we have very long-term use cases, of course, that will need still some years of research to be able to put this on the network. And for all these use cases, we are facing, of course, the problem of the adoption of the artificial intelligence by operational teams. So artificial intelligence is, of course, one step of, it's a form of enhanced automation. And the vision that we have today is that we are really in the beginning, and the journey is still long. We are trying to study and to bring to operations, individual use cases. We evaluate the use cases, I mean in orange and always, I think, in the literature, we evaluate the use cases based on the performance gain. But we still do not evaluate the performance of these use cases in terms of, okay, if I put this on the network, is it worth the effort? So the computational complexity, the storage that will be required. For example, I cannot put deep neural network everywhere in my network. I mean, it's just not feasible. We should take care of the information that should be exchanged on different interfaces, etc. And in my opinion, this would be the next step. The next step would be the integration of these use cases once we are done with the definition of the use cases to understand where AI could bring a gain. We should understand the cost of putting this AI on the network and putting all this together and how will it impact the network. So the AI use cases integration is something that is already, discussed. For example, in the ORAN Alliance, there is a working group dealing with defining the workflows and the interfaces that will be required for AI integration in the radio access network. And then the ultimate step would be to have this full network intelligence. That would be probably the 6G. So when we talk about full network intelligence, some people say, okay, I will design my new technology based not only on the exchanges of information that are needed for my communication protocols, but also on the information that are needed for the artificial intelligence. And all the network layer will rely on artificial intelligence. So to go back to the reality, today's reality, we have still big challenges with the availability of data. And the availability of data is not enough. We need also to have data of good quality, and this should be accessible also for, you have some problems, for example, in accessing data for research purposes, so this should be accessible for everybody. And then, as I said, we need to introduce the AI capability in the design of the technology. Because once we have proven that AI brings a gain, we definitely need to think about how to put this in a real network and to bring the theoretical solution towards real implementation. So many of the use cases that I told about are on the top of the OSS, taking the data reported by the network and doing some intelligent stuff. And this is, not an issue today to have this kind of solution, but once we want to put artificial intelligence in the physical layer, in the MAC layer, etc., in the infrastructure itself, we'll definitely need to think about the placement of the functions, about the impact in terms of computational complexity and storage capabilities. And we need to optimize all this together, not having use cases independently, but thinking about the optimal way to put all this together. And we need definitely to have people from different horizons working together, because if we give communication problems to data scientists, they will certainly find some good results, but which will not correspond to the problem, probably, sometimes. So we also, when I talk about skills, the opposite is also correct. We need communication people that understand AI algorithms. And we need to introduce not only performance KPIs, but also of the network, but performance KPIs of the algorithm, so that if something happens in the network, if something abnormal happens with an intelligent algorithm, the radio engineer or the telecommunication engineer is capable of understanding the problem. So be able to monitor everything in the network. And the last point, which is not the least, is the trust and adoption. So I told about technical solution to make operational teams trust AI. For example, being able of rollback or pre-training of the algorithm, so give guarantees to the operational teams that an artificial intelligence algorithm will not decrease to some extent the performance of the network, but we need also a cultural change, because I was talking about self-organized networks more than 10 years ago to some operational teams from Orange, and they didn't accept the concept. Why this automation will replace my expertise? Then they accepted to have this automation at one condition, understanding what is inside the box. So if you bring to them today a box that they cannot understand what is inside, but that doesn't take the same decision in time, even if nothing changes, because the box will enhance the decisions over time. How to test, how to understand, and how to trust. So that is, for me, the main challenge today. So I hope that I didn't take too much time, and I thank you for your
Thank you very much for the comprehensive discussion and a great set of challenges. I think we are a bit behind schedule. If there is a burning question, okay, or we can leave it for the next part, perhaps. So thank you, Sanna. So we enter in the part of the panel presentations in which we will hear the vendor opinions. So Henning will describe us Nokia's view with respect to how infrastructures will evolve, services, and also how they will benefit from AI.
Yeah, many thanks, Panelists, for having me in the panel. And I want to put a bit beyond 5G and AI into perspective. Beyond 5G, a new communication technology, AI, an enabling technology, and then for us, similar to Sanna's team, also the network automation aspects are particularly relevant. So let's get right into it. I think before we even think about requirements to communication, let alone an automation system, we need to think about scenarios, right? And here we try to outline two guiding scenarios. Guiding means, of course, they're not complete, exhaustive, right? But there are certain anchor points, and a lot of scenarios will then look quite similar, right? So what do we think are the driving use cases? And we have actually two categories here, a CSP, communication service provider scenario, and a non-public network scenario. The latter one is actually not strictly beyond 5G in terms of the underlying communication technology, but it's really in the B5G timeframe then, right? Okay, let's go to the CSP scenario in the application area. What are really potential applications driving this? And I think it's actually applications which are composed of different service components which have quite different characteristics. So meaning we cannot put them on one slide, eMBB or MMTC or CMTC, but it's really consisting of several things. One example could be, for example, remote emergency assistant for stroke patients, right? So there are only very few experts available, so it means you need to do it remotely, you need very high quality imagery, and you also need to have real-time control over what happens with the patient, even maybe if the ambulance is mobile. This is not possible today at all. So it's all around, and also this say, telepresence, remote presence of experts. And in terms of communication requirement, it really means a combination in the public network, so of ultra reliable, ultra low latency, ultra high throughput at the same time. And the problem is then, of course, that in principle, in an isolated way, probably we could or in a stationary way, we could make this available, but we need to enable this everywhere in the network, maybe not everywhere in the same form at the same time, obviously, right? Confer the emergency assistance scenario, but it needs to be available, so it means we need to be able to reconfigure or adapt the network to deliver such a huge performance, and so that means what I'm saying is it needs to be scalable to the wide area. Also then already coming a bit to the AI aspect, it needs to be very efficient with the human-machine interface, right? So that means the human operator should only be pointed to events which are really valuable and relevant for him, or where really this assistance is, or his assistance is needed. And I mean, we should not bother them with routine tasks, basically. Yeah? So the human resource is very precious, and we should really leverage the human knowledge, for the benefit then of how the machine-enabled networks operates. Yeah? Okay, so what does it mean for AI ML in network automation? So it's basically a platform thing, right? So we shouldn't build silos. We should build a platform where a lot of algorithms are already available. We can then configure to fulfill different functions, and also we need to have mechanisms for orchestration. Yeah, and that also translates to interfaces, devising workflows, governing the training, validating what the system is doing. All of or different aspects of that also, which are relevant then for standardization. And ultimately, that should then really yield some cross-layer optimization involving the RAN and the edge cloud. In particular, the edge cloud and the local RAN, due to this scenario, which are mentioned here, also going to the far edge, actually. Yeah. Okay, the non-public network scenario. Here we picked as an example an I4.0 industry scenario, basically with very frequent reconfiguration of production lines, and on one hand, on the other hand, also due to cost pressure, high optimization, for example, also AGV operations, again, where you have, for example, video uplink and very tight control constraints, so again, different service components together. And I think from network automation perspective, what is particularly relevant is the zero touch, simply because you will not have, really operational personnel for the network on site. It's just the usual IT personnel there or the maintenance personnel. So it's really about the zero touch of the RAN, also integrating into the local infrastructure, like for example, TSN. And what is, on one hand, a very good opportunity, but also then the challenge to really exploit is that we should actually try to do fusion of data, from the network domain and from the application domain. It's also what we typically don't do today in the CSP scenarios, because simply there's so many applications and so much different use of the network. Here we have really everything localized, we have everything under control, so it means we can actually not only exchange data, but also, for example, combine models, combine insights of these two worlds, right? And from the network side, I mean, we really need to be aware about the network state, because the requirements like latency are so tough. And on the other hand, also we should not see these islands in isolation, but we should really do transfer learning. So one thing I've learned, maybe in a certain factory environment, I can actually also transfer to the other one. And what you also can see from the picture from the table is that, of course, these scenarios are interrelated. So for example, from the application side, the moment I move out of the factory into the wide area, this is a logistics scenario, and then these scenarios are combined, and from the communication I need to interconnect also, of course, these local islands to form then, let's say, a combined company network. Okay, now going from the network infra to automation to applied AI/ML. So what we will see is, highly distributed network infrastructure, like I already mentioned, decomposed or more decomposition of RAN functions, fog cloud, a very scalable core. That means also when we go from, basically exemplified by going from millimeter wave to terahertz, beamforming device to device, so that all of this means that we have extreme but very volatile capacity. So that means we need to enable at that level multi-connectivity, quality protection to make this really viable. Then on the 5 meg area, we will see some usage of ML also there, like this channel model learning, but I think also yesterday we learned from Slavomir, okay, we really need to look at the use cases as usual. Then maybe the environment is also part of the network infrastructure, particularly in this more confined scenarios like a campus network. And also we believe then network slicing will be much more fine granularity, much more dynamic, like maybe every production line is then a slice. And we should have then this AI, ML specific processing capabilities everywhere. Now, how does it relate to network automation? I mean, Sana already mentioned there will be still this end-to-end management complexity, but of course we need to strive at the same time for simplification. We have the problem of distributed data, also distributed learning now, distributed computing with the associated energy consumption. And therefore, I think what is really important is that we manage network function slices not only in isolation, but really as part of their context, or with context as part of the environment, right? Like for this industry scenario. okay, use cases will come in the foreground like beacon configuration prediction, and then we need to manage, of course, the let's say, model creation, model management, or model distribution of the underlying layers. Okay, just to flash a bit technologies here for AI/ML, which also map to these different use cases. In terms of the network state, particularly autoencoder LSTM approaches are interesting because then you get a very compact representation you can use also for prediction. Reinforcement learning, I mean, in this optimization scenarios like the bread and butter type of learning algorithm, of course. Sana, I think, also mentioned distributed learning. I mean, in the sense of that we learn or we train it at certain areas in the network and then do the inference at other points possibly, and also transfer knowledge, right? Explainable models is very important, so that means the human, ideally as part of the model, the human should be able to, or should be tractable for the human basically, you know, what the model is really doing, and of course for deep learning this is not the case. And finally, we need also like a machine learning platform as part of the overall OSS platform in terms of orchestrating, pipelining, and potentially also standard interfaces.
Thank you very much. So I think there is consensus on many things that Sana and Henning have said. So now it's time to hear to Pei-Ning, Huawei view on the topic of ours. And then I believe it's obvious for the sake of time that we will take the questions at the end.
Okay. Thank you very much for inviting me to this panel. So I am going to talk a little bit more on the, actually maybe from different perspective, more on what we actually did not design the 5G for and why we need to look at some new things. So back 10 years ago when we started looking at what we should do for 5G, and at the time there are certain things, certain technology which actually are not there yet. But over the past 10 years, things progressed quite a lot. One of obvious things is this AI become a booming over the past few years. Actually, I try to put a picture there. You see the machine is becoming more and more intelligent. A human maybe becoming more dumb in certain ways. So if we look further toward 2030, maybe that trend is going to be even more obviously. So we were dealing with the AI, the equipment which has AI capability everywhere. Not only on the device, it's also on the edge, on the network. So that's something we haven't really planned when we designed the 5G system. Now, we're talking about the right now we're talking about how to utilize the machine learning AI technology to help the communication. Maybe by 2030, we're not looking at how to help the communication. Rather, we are going to design the communication to help the AI, how to do better AI systems. So it's really the not only the communication for AI also for communication, this kind of interplay there. Then the other things we haven't expected is we probably did not expect 2020. We didn't expect that we will have fleets of robotics deliver food, deliver the everything possible. So those machines are very capable. They need to be connected and so on. So, but this will become norm in 2030. I believe that will be. So therefore, we will see the need of the machine-to-machine communication, but this machine has quite a lot of intelligence. And the other thing, we look at the 5G was actually designed for car-to-car communication, but we only think about how to connect the car, how to enable the communication, but we probably did not look these are for the to the answer question. Research. It's very trivial. But there's some can and also theory of this machine learning.
Hi, thank Okay.
To 5.
Who wants?
And the be standard of the and will be and trying
items
This
Honestly, I don't really. Will really matching up. More. We knowledge to hard to actually, it's too complex. So you are mentioned about no correlation. Don't even know what's the theory, not even know model. Yeah.
Slavomir.
So maybe I can add. Okay,